Hey, you're looking at a thermal image of me. I figured that's about right for thermochemistry. What do you do on a day when it's 11 degrees outside and school gets started 2 hours late? You get up and you record some podcasts because that's the kind of teacher I am. Now, let's get with the chemistry. So, chapter 6 has everything to do with thermochemistry. In other words, when we run chemical reactions, some of them get warmer, some of them get colder, but all of them always involve a change in energy. These are the things you'll need to be able to do. So if you guys want to write them down or look at them or whatever, but in terms of for you to self-check and say, do I know what I need to know? You need to look and can you define these terms? And then can you perform these specific functions? All right, so all your life you've heard about energy, right? So energy is the capacity to do work. So anytime that you go outside and walk around, you're using energy, right? So there's a hippo down there, and that hippo requires a lot of energy in order to do the things the hippo does because it's big. And the thing on the right looks like energy just because it's awesome. I thought it was an awesome picture, so throw that in there. You've always heard about two different kinds of energy. Potential energy, like being on top of a hill, like being up on this roller coaster up here. For us, chemistry does not involve potential energy of position, but potential energy of composition, meaning that there's energy stored inside of a molecule, and that energy stored inside of a molecule can be released and used for other things. Right? So it's not that a molecule sits on top of a hill and races down like we've always learned about potential energy. It's more that has energy bound up in it. Kinetic energy is the energy of motion. That would be the roller coaster car racing down from that great big hill, or for us, that would be molecules moving around. And for us, kinetic energy is equal to 1/2 mv squared. But just a reminder that the energy, the kinetic energy measured of a molecule is equal to 1/2 its mass times its velocity squared. All right, now a lot of y'all say temperature and heat are the same thing, right? So temperature is just a measure of how fast the molecules are moving. But temperature and heat aren't necessarily the same thing. Heat is when one thing is warmer than something else. Heat always flows from hot things to cold things, from warm things to cooler things. Energy never flows backwards from cooler things to warmer things. Otherwise, all you'd have to do in the summertime is go outside and your heat would go to the outside and make you cooler, which doesn't make any sense. It'd be a nice world, but in order to warm yourself up, what you'd have to do is step inside the freezer. See, and that doesn't make any sense either. Temperature is a measure of how fast the molecules are moving. We'll use Celsius and Kelvin. Kelvin stops at 0, doesn't have any negative numbers. While heat, we're going to just talk about in terms of energy, and that energy will go from a warmer thing to a cooler thing, right? All right. The other thing I wanted to clear up is the law of conservation of energy. Now, all this time, you've been taught that to lose weight, you have to burn calories, right? So when you work out and you're running, where does all that weight go? And you say, oh, well, I burned it off as calorie. Well, that's not right because you can't change mass into energy. It's just not possible. You're not a star. You're not a nuclear reaction. So when you say that you're burning off the fat or burning off your body as energy, that's not right. What you're actually doing is going through a process chemically where you change the food into carbon dioxide and water. You're breathing out the carbon dioxide, you're peeing out the water, and that's how you lose weight. So if you want to lose 10 pounds, you're going to have to breathe out and pee out 10 pounds of carbon dioxide and water. Now, this does not mean you should start hyperventilating right now just to lose weight. You still have to convert the food from the food molecule into carbon dioxide and water. But just to get that out of the way, we don't turn food into energy. Now, heat is something called enthalpy, or enthalpy is a state function. a state function doesn't matter how you got there. Enthalpy is a change in energy, right? So when we talk about heat of a reaction, we're talking about the enthalpy, this word right here, of a reaction. And a state function means it doesn't matter what steps you took to get there, it just matters that you're there. Doesn't matter how you got to school. You rode the bus, you rode a car, you walked, you crawled, you flew in your airplane. Doesn't matter how you got there. The fact is, 8:15 in the morning when Mr. Parker comes on, the important fact is you're there. If you go to Vegas and you lost $400, doesn't matter. You could have placed one $400 bet and then gone home, or you could have placed 20 $20 bets and lost them all and gone home. You could have been up $500 and then down $100, and then up $500 and then down $1,300. I think that's right, but you can double check my math. But either way, you lose out. You're going home $400 poorer. The first law of thermo says the energy of the universe is constant, meaning you can't create nor destroy energy. And that's pretty much true, right? That's pretty much easy. So if you lose money in Vegas, someone else is making it. The amount of money is constant, right? We'll just make believe that's true. Delta H, delta means change. H means heat, right? The enthalpy, change in energy, we're going to say is delta H. Wood burning, that has a negative delta H because that's releasing energy, right? If you're doing something where you gain energy, you absorb energy from your surroundings, that's a positive delta H. Isn't that a lovely piece of bacon? All right, next slide. All right, we can look at heat in two different ways. We can say specific heat in terms of grams, or how many joules, that's energy, does it take to make something change temperature per gram of that substance, right? Or we could say the same thing, how many joules does it take to make something change temperature per mole? Doesn't matter if you do it per gram or per mole, but one is specific heat and one is molar heat capacity. I love me some snickerdoodles, don't you? They actually have cream of tartar, which is actually an acid that they scrape off the inside of wine barrels called tartaric acid.